Okay. Okay, if I go ahead and turn on the projector here. So if you look at what's going on with our what we have here, we have a position versus time graph. It's similar to the one we have for our lab, only that now that we have a negative position in this way. So we have let's just say this represents somebody walking along as time goes by. There's 7 segments, A through H, and we're going to try to find the velocities of that. We should know from the lab that if we can find the slope of a position versus time graph, we can find the velocity. So we have some questions down here about distance, displacement, speed, velocity, average, all of those. But first we're going to fill out this over here. So calculate the velocities of each of the individual line segments A through H by finding their slope. Right? The slope is a decimal rounding out to 2 decimal places, including units here. So first thing we want to when we're trying to find the slope of these lines and think about what's happening here, we want to look at how much each box is worth. So up and down, each box is worth how much? If you look here. Yeah, they're worth 10 meters. And then side to side, how many seconds is each box worth? Yep, 2.5, so 2.5 seconds there. So we have those two there. Notice that because when we flip over to the graphing practice number 2, it's different up and down. It's only 5 instead of 10. So just there's always kind of look over and to make sure you're doing the right thing. Now, what does this kind of represent? A lot of times we think of these, this may be where the person started. So you may say, well, that's the origin. Well, we tend to think that this 0 line is the origin. So sometimes we'll have things where you'll try to maybe make up a story about what's happening here. Let's say that maybe this is, I've been using this is your home. So this is where you start, this is where, wherever your home is here. So first you start out away from your home, let's say in the negative direction, or it's basically, left of wherever you live, okay? And then you just stand there for a while, and then you walk away, and maybe you suddenly remember you forgot something, so you start walking back. You realize you're getting late for there. You run back. You grab what you need, you keep going in this direction, and you're like, hey, I gotta get to school. You pause, you think maybe I left something, so you start walking back. I don't know, maybe you pick up some food, so you start walking back slower, and then you're like, oh yeah, I had to go to school, so you run off of there again. So it doesn't work exactly, but you can kind of get an idea where this is kind of where every time you cross this origin, you're back at home, or it's some place where everything is measured relative to that point. So we need an equation for the slope of how we're going to find this slope. Got so much stuff here. I'm going to move it back. All types of documents here from my document camera. Okay, so the equation we're going to have for finding our velocity here is basically how you would find your slope. So V, we have x of f minus x of I over t of f minus t of I. So x represents our position, at least in terms of moving horizontally, and t is our time. F is the final, and I is the initial. So those are the big things. We're trying to measure the differences and stuff, especially differences in position. It's always final minus initial. Okay, always final minus initial. Yeah, question?
Is t like an exponent of I?
No.
I is a subscript.
Yeah. F and I are subscripts of t. Yep. Okay, good question there. So we're going to use that when we're going through this. Okay, so we're going to start with A here, and there's not a lot of room to work here when we're writing our notes, and that's the best that I could do with make sure we still had a big enough graph that we could look at. So I'm going to basically do the work up here at the top, the A, and so you could choose, if you wanted to maybe try to put all the work on the same page. That would be pretty busy. That's basically what happened with this, and it just got out of hand. That's what I did before school. So kind of keep it in order. I'm going to do A, B, C, D up here, and then E, F, G, H inside of there. So To start off with A, we always want to look at the final position. Now, you may look at this and say, well, isn't the velocity 0? There's no slope here. Yes, but I still want you to kind of think about it using it in terms of this equation so we get used to this. So if we're looking at the final position, which is right here, what is the final position of this person, for this segment here? What's the number? Negative 60, yeah. So negative 60 minus, and where did it start? Yep, negative 60 again. So negative 60 minus negative 60. I like using parentheses there so I don't lose track of which things are my negatives, or which parts of my numbers are negatives. And then for time, we want to now be looking at time. The final time was, what, 10 seconds here? And then it started at 0, so 10 minus 0. So negative 60 minus the negative 60. Cancel those two negatives out. I get negative 60 plus 60. Obviously, we knew that was going to be 0 over 10. Here's what I minimally want you to write. So once we get that 0 to 10, I want you to go over here at A. Don't just write 0 automatically. This is an important step for you to figure out how to do these extremely easy later. So write that part 0 over 10. It's the same part that we have up here at the top. And then we're going to actually calculate what that is. So 0, and then units would be 0 meters per second. So you do the work up here. You calculate sort of this little part here. The reason why this is important is this gives you how far you've gone on the top and how much time it took, which is very important for finding how far you went and then ultimately how long it took. So we'll look at B, C, and D together, and then we'll talk about how to do the ones on the bottom. So B here, when we look at, when it's have this line, I like to draw a box, or not a box, but a triangle, just to kind of better visualize what I'm seeing here. Doesn't have to be on the bottom, could be one that goes up on the top here, same thing. So we're looking here, what is the final position here? We're not in terms of time, but we're looking kind of in terms of, sometimes it helps to use a ruler as well, if you want to, like, what is the final position that it's at right there? What is that distance, or what is that position? Yeah, negative 90, so for B up here, we got negative 90 minus, and where did it start at for B?
Negative 60.
Yep, negative 60. Okay, that's that. Sorry, negative 60. And then for time, we can see here it ended at 20 seconds and started at 10, so that is 20 minus 10. The reason why it's really important we always do final minus initial is that if you flipped and you made it initial minus final, your signs would be all off in basically which direction you were traveling in. It's not always going to be a positive number. This one, in this case, negative 90, basically plus 60 is negative 30. Oops. And 20 minus 10 is 10. And so once I get that, I go over here, put negative 30 over 10, and that's negative 3 meters per second. Remember, negative 3 meters per second doesn't mean this person found some way of walking slower than 0. It just means they're walking 3 meters per second in the negative direction. So it could be going backwards, it could be going left, it technically could be going down, but in this case, position with X we usually mean side to side. Hey, now let's look at C here. So I'll draw my little triangle to help me better visualize what's going on there. So for C, what is my final position here? It's close here, but if we look at it, negative 30, because it's negative 20, then negative 30, negative 40, so negative 30 minus where we were here, we started, which was negative 90. You're going to start seeing kind of a pattern, especially when you write your workout side by side. Notice here, if you look here at the top, your initial speed you have for this segment here is actually the final that you had for this segment. The initial you had for this segment was the final you had for this segment. So you're going to see parts of positions and times that were in the other ones. Because why? Why would you see that? Why would that make sense to see them in other ones, these numbers here. They're all connected. They all lead. There's not a gap. It's not like suddenly it skips over here. You have good. There's a gap. So our time frame here is from 40 seconds to 20. So 40 minus 20. Okay, cross out my negative. So negative 30 plus 90. So that's 60 divided by 20. So go down here. 60 divided by 20 is 3 meters per second. Now, that basically means that B and C here have the exact same slope. It's just that B is going in the negative direction. It may be hard here to see that they have the same slope, but if I basically run it for the same amount of time as the other one, you can see here that this line and this line are the exact same slope. They're just opposite. So it's perfect kind of V here. It's a perfect sort of bouncing off. The only reason it doesn't look exactly like it is that it runs for a further longer time, but the slope is the same. In terms of its magnitude, it's just a different direction. The last one we'll look at here is D before we talk about how to find the distance and displacement and the other ones. So there's my little triangle, D up here. So now we're crossing from the basically from the negative side to the positive side. So my final here is what? What? Somebody said it. It's 30. Yep. So 30. So 30 minus where we ended up here, or for end of C would be negative 30. So 30 minus negative 30 over the short time frame. So this is 45 seconds here, but in between that means that this would be 42 and a half. So 42 and a half minus 40, we end up with 60 over 2.5. That's a pretty big number, so we're 60 over 2.5. And I think that comes out to 24. So if you saw that, you might be like, oh, maybe I made a mistake somewhere because I have 0, negative 3, 3, and then suddenly out of nowhere, 24. But if you had to look back at the graph, what about this line segment says that, you know what, that kind of makes sense. That definitely makes sense. What about it? What could you say about the line that says that it makes sense that this number is so big? Yeah, in the back? Yeah, it's very steep. Yep, it's extremely steep there. And also with the other ones, if you were just looking here, you could say, well, what kind of number should they have here? Should they be positive or negative? Well, that has none, so that's 0. That's going in the negative direction, so that's negative. That's going in the positive direction. Even though it's inside the negative area, it's going positive, so that's positive, and then that's positive there. So I'm going to have you complete the rest of them in a second. Let's look at how to find the distance and displacement. So I'm going to fill this in. Oops, not with that one here. Yeah, I'm going to replace this with one that I solved this morning. Okay, yeah, it has. Yeah, it's a lot more messy. I was like, I need something better because you're probably not going to be able to read all that as clearly. So these four, obviously, they're here. I still want you to calculate them the same. But let's look at the distance and displacement, how you figure that out. Remember what we talked about yesterday where distance is this additive total that's always going to increase and increase. It's not like you can take a step back and your distance goes down. You take a step back, your distance just keeps going higher and higher and higher. So it's basically, it wants to know how far you traveled, but it doesn't care which direction because it's always just adding up. So if you look at these, it's basically taking all these numbers on top. Remember, these are all how far it traveled. How far it traveled, and then if it has a negative, which direction. So distance doesn't care about the direction you're traveling, and all it cares about is how far you traveled. So if you look at actually the difference between that and displacement, displacement cares not only how far you're going, but also what? Which direction you're going in. So it's not like I'm ignoring the negative numbers here. I'm just or the negative numbers here. I'm just ignoring the direction. So we see over here we have 0 plus 30 plus 60 plus 60 plus 0 plus 30 plus 20 plus 90. That's why I find my distances. I just basically ignore the direction of which way they're going, and then you add all that up. And then for displacement, you're taking the same exact data, but now you're including the direction. So basically this almost means like 0 plus 30 to the left plus 60 plus 60 plus 0 plus 30 to the left plus 20 to the left plus 90, where this one just doesn't care what the direction is. So we can see here that the 290 obviously is going to be greater than 130. There's here thought question here. What's the only way in which you can walk so that your distance and your displacement are exactly the same? Yeah, well, in a straight line. So it's the only way it's possible is in a straight line. If we saw this here, if I just walked 10 meters in a straight line, the distance would be 10, the displacement would be 10. The moment I change my direction, let's say I walk backwards, distance is like, hey, just keep adding to the tally. It's 11 here, where displacement says, oh, it's 10 minus 1, and so we get 9. Same thing as well if you change your direction another way. You may walk 10 and then walk 3, your distance would be 13, but how we would find this is that we would use this to figure out the hypotenuse using Pythagorean theorem, and we actually take that further in lessons that'll come in weeks and weeks from now, where let's say we have this complicated path and we start here and we end up here, and I want to know exactly how far away that is, and also compared to a unit circle how many degrees that would be here. So it's basically kind of splitting all of these up into their x and y components, but that's all for another day. So yeah, the only way your distance and displacement can be the exact same amount is if you walk in a straight line and never change your direction or anything like that, which obviously is a straight line. So last thing down for average speed and average velocity. This is why I had you write that down. If you just recorded, for example, 0, -3, 3, all those, you would have to basically redo the calculations all over to figure out these. And so for average speed, it says it's total distance over total time. 209 is your total distance. Your total time is 75. So you divide those two. And then for average velocity, velocity goes with displacement. We want direction on this. So because we say, well, why necessarily is this less? Okay, you could be. I'll say here. You could be. Think about. Let's say if you drive your car. And let's say you park it out in front of your parents' home or whatever, and you drive to school, you maybe drive to work or drive to practice, but ultimately, even though you may be going, at sometimes 60 on the highway and 10 here and 25 in the school zone, if you got home and you parked your car in the same spot, even if you may have exceeded speeds, really fast or really slow, your velocity is going to be 0 because you didn't displace yourself anywhere. So that shows a really big difference between average speed and average velocity on those. Okay. So I'm going to give you, basically we have, that's basically where I stopped for the other ones, and filling those out. So doing the work for E through H. So I go back to this other one. So going back to E through H, I can put back the other document, filling that out, and then basically once you fill that side out, practice 2 is homework, but we have a longer period, but other classes got it done with like 10, 15 minutes left. So that's that. I'm going to stop it there. So